Hello there, and welcome to the Dreamology channel. Tonight, we're gently drifting back toward the very beginning of everything we know. Long before stars began to shine, before galaxies slowly turned through space, before time had a steady rhythm or space had a familiar shape, the universe began its quiet and mysterious journey. The Big Bang is often imagined as a sudden explosion, but in truth, it was nothing like a blast in empty space. It was the universe itself expanding from an extremely hot, dense beginning. This story is not just about origins, it is also about connection. The atoms inside your body share a direct lineage with those earliest moments. The same physical laws that shaped the first galaxies are still shaping the world around you right now. As we explore this vast beginning together, we'll move through discoveries that stretch the imagination, and we'll touch mysteries that science is still gently approaching, rather than fully answering. If you enjoy these calm journeys through space and time, you're always welcome to like the video, subscribe, or leave a quiet thought below. It helps other wandering minds find their way here too, one sleepy soul at a time. For now, there's nothing you need to do. Let your body soften. Allow your breathing to slow. Let the weight of the day begin to fade. Tonight, we're simply exploring the origins of the universe together. Let's begin. The Big Bang does not describe a bang at all. It describes an expansion. What makes this idea so powerful is not drama, but evidence. The Big Bang is not a myth, and it is not a guess. It is a model that brings together several very different observations into one calm, consistent story. When we look out into space, we see that distant galaxies carry light that has been stretched toward longer, redder wavelengths. And the farther away those galaxies are, the more that stretching appears. This pattern fits naturally with an expanding universe. When we measure the faint background glow that fills the entire sky, we find radiation that matches exactly what a much hotter, younger universe should have left behind. And when we examine the lightest elements found in ancient clouds of gas, their proportions align with what a young, hot cosmos would have produced in its earliest moments. Taken together, these clues turn the Big Bang from a bold idea into a story that can be tested, checked, and refined. The Big Bang is not just a beginning frozen in the past. It is a framework that continues to be measured against the sky itself, and it leads us to one of the most important clarifications of all. The universe did not explode into space. Space itself expanded. When we hear the word expansion, it's natural to picture an explosion. Debris flying outward into an empty room. But the universe did something far stranger. There was no empty room waiting outside. The room itself grew. In an ordinary explosion, matter rushes outward from a central point. In the Big Bang, space itself began to stretch everywhere at once. That difference explains something subtle and important. There is no special center of the universe you could point to, no hidden origin spot marked on a cosmic map. Every region of space sees distant regions moving away, not because they are racing through space, but because the space between them is gently stretching. This idea also explains a famous curiosity. Very distant galaxies can appear to recede faster than the speed of light without breaking the rules of relativity. Nothing is actually outrunning light locally. Instead, the distance between faraway places is increasing. You can imagine it like dots drawn on a rubber sheet. As the sheet stretches, the dots move apart, even if they never slide across the surface. This way of thinking changes how we picture the early universe. Matter did not burst outward from a single point. Instead, the entire universe was once smaller, hotter, and denser everywhere, and then expanded and cooled as a whole. At first, the universe was remarkably smooth. Energy and particles were spread almost evenly, with only tiny differences from place to place. If it had stayed perfectly uniform, nothing interesting would have formed. No stars, no galaxies, no structure at all. Gravity needs small irregularities to work with. And the remarkable thing is that those tiny variations did exist. They were incredibly small, but they were enough. Over immense spans of time, slightly denser regions pulled a little harder on their surroundings. That extra pull drew in more material, making those regions denser still. This slow feedback process transformed faint ripples into real structure. Gas gathered into clouds. Clouds ignited into the first stars. Stars collected into galaxies. Galaxies assembled into clusters and long filaments. When you look up at the night sky, you're seeing the grown-up version of those early, nearly invisible differences, magnified by gravity into a universe full of shape and pattern. And woven through all of this is the oldest light we can still observe, light that began its journey long before stars existed. The oldest light we can observe still fills the universe today. It arrives from every direction, quietly and steadily. This light began its journey when the universe finally cooled enough for atoms to form. Before that moment, space was filled with free electrons. Light could not travel far without constantly colliding with them. The universe was bright but opaque, like a glowing fog you couldn't see through. Then, as expansion continued, temperatures fell. Electrons settled into stable orbits around nuclei. Atoms formed, and suddenly the universe became transparent. Light was free to travel long distances for the first time. Those ancient photons have been moving through space ever since, crossing billions of years to reach us now. Over time, the expansion of the universe stretched their wavelengths. What began as hot, energetic light slowly cooled. Today, that ancient glow reaches us mostly as microwaves. By studying this all-sky background, scientists are not looking at stars or galaxies. They are looking at a snapshot of the universe before any of those objects existed. It is a picture from a time when the cosmos was still young, smooth, and simple. This faint afterglow is colder than deep space, yet it is everywhere. Even what we think of as empty space has a temperature set by this ancient radiation. It forms a quiet thermal fluor that fills the universe. The glow is invisible to our eyes, but sensitive instruments can measure it with astonishing precision. And it appears in a surprising place. A small fraction of the static once seen on untuned television screens came from this same cosmic source, arriving after a journey that began long before Earth formed. The background light is also remarkably uniform. That smoothness tells us the early universe was well mixed. At the same time, it contains tiny variations, subtle patterns that act like a map of primordial conditions. In this sense, the coldness is not emptiness, it is information, a record left behind by a universe that was once far hotter and denser than anything we see today. For a brief time, the universe was hotter than Even the most massive stars reach temperatures of tens of millions of degrees. The early universe was far hotter than that. At such extremes, atoms could not exist. Even atomic nuclei could not survive. Matter became a restless sea of fundamental particles and radiation, constantly interacting, forming and dissolving in an unbroken flow. In this environment, familiar distinctions faded. Energy turned into particles. Particles turned back into energy. The universe was not a collection of objects. It was a changing state of physics itself. As expansion continued, temperatures slowly fell. And as the universe cooled, the set of particles that could exist began to change. Some types became rare. Others dropped out of equilibrium and remained. That is why these earliest moments matter so much. The physics of this era helped decide which ingredients the later universe would have to work with. When scientists build high-energy experiments on Earth today, they are not only smashing particles together, they are briefly recreating echoes of this primordial heat. Within the first few minutes, the universe forged most of its helium. Helium is often associated with stars, but a large fraction of it formed before the first star ever ignited. As the cosmos cooled, protons and neutrons began to bind together. This window was narrow. The universe was hot enough for nuclear reactions, yet cooling quickly as it expanded. Helium proved especially stable, and most free neutrons became locked inside helium nuclei. That is why roughly a quarter of the normal matter in the universe today is helium. Alongside hydrogen and helium, small amounts of deuterium and traces of lithium also formed. These abundances are not random. They depend sensitively on how much ordinary matter existed in the early universe. By measuring light elements in ancient, relatively untouched gas clouds, scientists can test the Big Bang model with remarkable precision. Every atom in your body traces back to this history. Some of your atoms were shaped during these first minutes, when the universe was still young enough to act like a giant nuclear furnace. Others arrived later, forged inside stars that lived, aged, and transformed. Together, they tell a layered story. The early universe provided simplicity. Later cosmic generations added complexity. When we talk about the age of the universe, we are not counting years in the usual sense. Cosmologists do not mark birthdays. They read time from the expansion of space itself. By measuring how fast galaxies move apart at different distances, scientists reconstruct how the expansion rate has changed over cosmic history. Expansion leaves several kinds of records. It stretches the light traveling from distant galaxies. It sets the size of faint patterns imprinted in the early universe, and it influences how structures grow over time. When these independent measurements agree, they form a consistent timeline. That is how we can say the universe has an age at all, even though no one was there to watch it begin. This approach also explains why small disagreements matter so much. A tiny change in today's expansion rate reshapes the inferred past, and it can hint that something important is missing from our current picture. In the earliest eras, the universe was so dense that light could not move freely. Imagine trying to see through a storm where every beam of light is scattered instantly. Early space was filled with charged particles moving at high speed. Photons existed, but they could not carry images across long distances. The universe was bright, but opaque. This creates a natural limit to what we can observe. we cannot see earlier than the moment when light finally began traveling in long, straight paths. Before that, the universe was not dark. It was too hot, too bright, and too crowded to be transparent. As expansion continued and temperatures dropped, electrons were finally able to remain bound to nuclei. Atoms formed, and the universe changed character. Light decoupled from matter and began to stream freely. This moment released the oldest light we can observe today and set the universe on a new path. Neutral gas behaves differently from a charged plasma. Pressure dropped, cooling became more effective, and gravity could finally begin gathering matter more efficiently. A small change in microscopic behavior reshaped the destiny of everything on the largest scales. This is why the early universe can be studied like a fossil. A single transition left a sky full of information, and we can still map it with remarkable precision. After the universe became transparent, something unexpected happened. For a long time, there were no stars at all. The first atoms had formed, the oldest light had been released, but space did not immediately fill with shining points. Instead, the universe entered a long, quiet period known as the Cosmic Dark Ages. During this time, space was filled mostly with hydrogen and helium gas. Gravity was slowly at work, gently pulling matter into denser regions. But nothing had ignited yet. There was no starlight, no glowing galaxies, only darkness in the everyday sense. This long pause mattered. It was a time of preparation. Invisible scaffolds of dark matter deepened. Gas gathered patiently inside them. Dense regions grew denser, almost imperceptibly over millions of years. The Dark Ages are difficult to observe directly, which makes them one of the most intriguing frontiers in cosmology. When we learn how to listen to signals from this era, we will be hearing the universe before its first lights turned on. Eventually, the first stars formed. They ended the Dark Ages by flooding space with light. These early stars were not just new objects, they were cosmic switch flippers. Their intense ultraviolet radiation began stripping electrons from surrounding hydrogen atoms, turning neutral gas back into an ionized state. This process is called reionization. It did not happen everywhere at once. It spread outward in growing bubbles around young stars and early galaxies, gradually overlapping until much of the universe was affected. These first stars also began forging heavier elements inside their cores. When they died, some of that material was scattered back into space. In this way, they were both beacons of light and chemical pioneers. They transformed a simple universe into one capable of greater complexity. Without them, planets, chemistry, and life would never have been possible. The first galaxies did not appear as the graceful spirals we see today. They began small. Early galaxies were modest gatherings of gas, stars, and dark matter, forming along the filaments of the cosmic web. Gravity then did what it always does. It pulled. Small systems drifted together. Mergers were common, and those encounters were creative in a rough, untidy way. When early galaxies merged, gas was stirred and compressed. New waves of star formation followed. Growing central black holes were fed. Over time, repeated mergers built larger and more structured galaxies. This is why the deepest images of the early universe show irregular, clumpy shapes. They are snapshots from a restless era, when galaxies were still assembling themselves. Our own Milky Way carries traces of this history. Streams of stars in its outer regions likely came from smaller galaxies that were pulled in and absorbed long ago. A galaxy is not just a collection of stars. It is a family tree written in light. On the largest scales, the universe resembles a web. Galaxies trace long filaments, clusters form at intersections, vast voids open between them. This structure was not designed, it grew. Tiny early irregularities were amplified by gravity over billions of years. Where matter was slightly denser, it attracted more. Where it was slightly thinner, it was left behind. The result is a universe that looks textured rather than smooth. What makes this especially striking is that the same structure appears in computer simulations. When scientists begin with tiny early fluctuations and allow gravity to operate, the resulting cosmic web closely resembles what telescopes reveal. It is as if we are watching the universe assemble itself again. And through it all, the expansion of space continues quietly in the background, shaping how fast structure can grow and how the future will unfold. For a long time, scientists expected gravity to slow the expansion of the universe. It seemed reasonable. If everything began moving apart, gravity should gradually pull things back, like a ball tossed upward that eventually falls. But observations revealed something unexpected. The expansion of the universe is not slowing down, it is speeding up. This discovery came from studying distant exploding stars, known as Type Ia supernovae. Their brightness follows a reliable pattern, which allows astronomers to measure vast cosmic distances. When these explosions were observed far away, they appeared dimmer than expected. The simplest explanation was surprising. The universe was expanding more slowly in the past than it is now. Something is causing expansion to accelerate. We call this influence dark energy. Dark energy does not behave like ordinary matter. It does not clump or form structures. It appears to be tied to space itself. As space expands, more of this energy seems to come with it. If this picture is correct, it changes how the future of the universe unfolds. Over immense spans of time, distant galaxies will slip beyond a cosmic horizon. Their light will never reach us, not because it stops being emitted, but because the space it must cross stretches too quickly. The universe does not end, but the observable universe grows smaller from our point of view. Local regions remain intact. Galaxies bound by gravity can still orbit, merge, and evolve. Stars will continue to form for a time, but on the largest scales, the cosmic web slowly loses its ability to tighten its threads. This future feels quiet, not catastrophic, not dramatic, just vast, patient, and increasingly empty. It reminds us that cosmology is not only about where we came from, it is also about where the universe is gently heading. What makes the Big Bang model so compelling is not any single discovery. It is the way many different lines of evidence quietly agree. Expansion shows up in the redshift of galaxies. Light elements appear in proportions that match a hot early phase. The faint background glow carries the thermal signature of a young, dense universe. And large-scale structure shows how tiny early differences grew over time. Each of these clues comes from different tools, different observations, and different methods. They do not rely on the same assumptions. They do not share the same sources of error, yet they converge. That convergence is the real achievement. When one measurement disagrees with another, cosmologists do not panic. They lean in. Attention can mean a hidden systematic error, or it can mean new physics waiting just beyond the current model. This is why modern cosmology keeps evolving. The model is not protected from questions, it is sharpened by them. One of the most famous early shifts came when astronomers realized that galaxies are not all part of the Milky Way. For a long time, spiral nebulae were thought to be nearby clouds. Then distance measurements showed they were far beyond our galaxy. In a single step, the universe expanded from one island of stars into a sea of islands. Soon after, the stretching of light from distant galaxies revealed that space itself is changing. Distances grow. The universe has a timeline. That realization It ties together early heat, element formation, and later structure into a single, consistent narrative. The Big Bang model works because it makes predictions that can be checked. And again, when the universe is asked the same question in different ways, it gives the same answer. The Big Bang model tells us how the universe evolved from an early, hot, dense state. It does not automatically tell us what came before. When people ask what happened before the Big Bang, they are asking a deeply human question, and physics answers with care. In many versions of modern cosmology, time itself is part of the story. It emerges along with space. If time begins with the early universe, then the word before loses its usual meaning. It is not a place you can point to on a timeline, because the timeline itself is what is coming into existence. That does not mean curiosity is unwelcome. It means we are approaching the boundary where our current theories stop being reliable. To go further, scientists search for deeper frameworks that can describe the earliest moments without breaking down. Until then, cosmology stays honest. It describes what can be tested, and it avoids inventing what cannot. Some ideas imagine that the universe did not begin with a singular start, but with a transition. In these models, the universe may have once been contracting, then reached a turning point, and then began expanding. In that view, the Big Bang is not the absolute beginning, it is a change of direction. These ideas are appealing because they might avoid an initial singularity and help explain why the universe looks so smooth on large scales. But they also face serious challenges. At extreme densities, known physics may not apply, and it is difficult to understand how information from a previous phase could survive such a dramatic transition. Other proposals suggest that rapid early expansion, known as inflation, played a key role. In this picture, a tiny region of space expanded extremely fast for a brief moment. That burst of expansion could explain why distant regions of the universe look so similar, and why space appears nearly flat. Inflation does not remove all variation. It leaves behind tiny fluctuations with specific patterns. Those patterns later grow into galaxies and clusters. This makes inflation testable, not just imaginative. When scientists compare its predictions with detailed maps of the cosmic background, they are asking whether the universe behaves as if it truly experienced that early growth spurt. The answers so far are suggestive, but not final. At the edge of knowledge, cosmology becomes both cautious and creative. It balances wonder with restraint. We may never watch the beginning directly. The earliest moments of the universe remain hidden behind conditions so extreme that our current theories reach their limits. And yet, the universe has been leaving evidence ever since. Ancient light still fills the sky. The lightest elements carry records of early nuclear reactions. The distribution of galaxies traces how tiny differences grew into vast structure. These are not separate stories. They are cross-checks. If the early universe had been different, the sky today would look different too. That is why modern cosmology feels so grounded. It is not built on a single observation. It is built on many independent records that quietly agree. The universe is still expanding. This is not just a historical event. It is the present tense of the cosmos. Distances between faraway galaxies continue to grow. The rate of that growth is shaped by what the universe contains. Over immense time, expansion changes what kinds of interactions are common. It affects how often galaxies collide, how easily matter can gather, and how the cosmic web evolves. If cosmic acceleration continues, the distant universe will slowly fade from view, not because it disappears, but because space itself grows too wide to cross. Future observers may see a quieter sky. Yet here and now, we live in a generous moment, a time when ancient light is still visible, when the cosmic background can still be measured, when the universe still offers clear clues about its past. In that sense, cosmology is also a story about timing. The universe reveals its history for a while, and then geometry slowly hides parts of it away. The Big Bang is not only a story about a beginning, it is a story about unfolding, about a universe that continues to stretch, cool, and change, turning simple beginnings into long, patient futures. And in that fast, slow movement, there is room to rest, room to let go of urgency, room to soften the edges of thought. You don't need to solve the universe tonight. You don't need to hold every idea in mind. Let the images fade. Let the questions drift outward like distant galaxies. The universe has been here for billions of years. It will continue long after this moment. For now, you are simply part of the quiet present. If these gentle journeys bring you comfort, you're always welcome to explore another one waiting nearby. And if this space feels like a place you'd like to return to, you can like the video, subscribe, or leave a thought below. But for now, there's nowhere you need to go. Allow your breathing to slow. Let the day dissolve. You've done enough. Sleep well, and good night.